Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My pleasure to introduce Gilles. Yeah. Okay, my French is pathetic, okay? Like, so pathetic they pay me not to speak French when I go to France. So I won't even try to pronounce the name of his school again.
Yeah, that's good. It does not matter.
That's good. See, he's heard me attempt it, so that's why he says that's good not to try it. But lovely location in Brittany is where, so
yeah.
So he gave up Brittany to come here to speak to us.
It's as sunny as here.
As sunny as here. Oh, well, then it's got to be lovely. Anyway, who's here to talk to us about drivers and finding code, where code goes, and lots of things like that. So
yeah.
I'll turn it over to you.
So my talk is about evolution in drivers and how we try to solve the evolution problems. So it's really about Linux. So I'm sure it's a problem you don't have here at Microsoft.
No driver evolution.
But anyway, so this is really a distributed work because strangely my closest colleague is Julia Lawal. And okay. Okay, so she's working in Denmark and I'm working in France, and we are making an extensive use of MSN. So thanks, Microsoft. So the name of the project is Coccinelle. One thing I should say is I'm really an operating system person, and Julia is the programming language one. So if I'm telling mistake about programming language, please don't throw tomatoes and everything else. So what's the problem we are targeting? So the problem is what we call collateral evolutions. Collateral evolutions are the result, it's a side effect of an evolution of in a library. So let's say we have a library, lead.c, that contains a foo procedure that later on becomes bar for whatever reason. Problem is that now you need to update all clients, and everywhere you have to replace foo by bar. So this is a really simple example. It gets much more complicated when you add parameters, remove parameters, change structures, and so on. And this is a real problem in Linux, or Linux, I don't know which one you prefer. So, and it's a real problem in Linux device drivers. Why? Just because there are many libraries everywhere in Linux drivers, and there are many drivers, maybe not as much as in Windows, but still there's a huge number of drivers. And right now it's about a little bit more than 50% of the total size of the code. And for 1 year, we've done extensive domain analysis of the problem in Linux driver. Some of our results have been presented at Eurosys 2006, and the problem is getting worse with new version of Linux. So more and more there are evolution in libraries and, of course, collateral evolutions. And it's going to be even worse in the future, just because the people in Linux, they decided to evolve much more the internal APIs just for having a kernel that is that matches the evolution of the driver. So they really want to be highly efficient. And for that, they don't hesitate to break existing interfaces.
This is like really good news for us and like really good news for researchers who want to work on software update. But really, I mean, why? I mean, is it just because they can? I mean, don't they get back pressure from the Red Hats of the world and the integrators? I mean, I just can't. I don't quite understand the dynamic. I mean, like here, there's a huge back pressure to like be backward compatible to Windows 2000, the WPDM interface, and
I know.
And why is that back pressure there?
I don't know. I'm not part. I'm not part of of this crowd, and Linus is not my next working person. But I think their motivation is really to be as efficient as possible, and they want to match as much as possible the evolution of the hardware. So if there's a better software structure to come up with something that appears in a recent driver, then they want to be free to have the best possible software for that. So.
Well, you can recompile it yourself.
Anyway, so we've done a taxonomy of evolution, and so these evolution are adding an argument, changing the shape of data structures, adding getter or setter functions, changing the protocol. This is quite frequent. Change of the return type, add error checking, or change the way error checking is done. These are really frequent. Yeah.
I'm not clear here on whether you're talking about evolving formalized APIs or just that these are the kinds of changes that people make within subsystems. That, you know, there might be a new version of a driver, and what kinds of changes did they make? Oh, they made all these changes, and that has to percolate through the whole.
Okay, so
or are you talking about formalized APIs?
I'm not sure there are real formalized API within the kernel. So
they're sort of semi-public. These are interfaces
exactly.
between.
So the way it works right now, there's someone who's responsible for a library and its evolution, and sometimes they decide for some reason that it's better to change things. And there are many libraries like that for PCI, sound. There's frequently one library per type of bus and so on.
Okay, so these are changes. The interfaces into a software component, but it hasn't been strongly formalized.
Yes.
It sounds like this would be kind of similar to our mini ports. So, you know, the mini port. So we have this model. Yeah. So, for example, SCSI device drivers. There's a lot of common things that happen with SCSI device drivers. Yeah. And so there's a port, which is the device driver the system sees, provides, knows how to do SCSI, and then there's a small plugin that does the specific things for an adapter. And it sounds like you got a very similar.
Exactly. So you have many common libraries, and each device-specific code uses one or several libraries. I have numbers if you want to see them. They come from the Eurosys paper, and a device-specific code can use up to 6-8 libraries. Okay, so here's an example, a very quite simple one. So it's about a CSI, and get and put function have been dropped from the library interface, and now the parameter is now part of the signature of the procedure. So to perform this collateral evolution, in every client code, we have to remove get and put, and also we have to move the declaration of Y to the procedure.
Are these dynamic link libraries or static link libraries? Are these things that you just get to use sort of as a convenience when you're developing a driver, but
Yeah.
they end up in your code, or are these DLL-like things?
I think it should be both cases. But for most, well, it really depends on the way the driver is packaged. It can be packaged as a single big Linux module, or maybe a set of several ones.
It seems like if it's a static library, well then this is sort of hidden inside the driver. And so, well, it's an annoyance for writing the driver, but it's the problem of the person who writes it. And if it seems like if it's a dynamic link library, this is Linux's version of DLL hell, right? You have different revs of drivers. They want different DLLs. You have to have them all present. You have to keep the version straight.
Yes and no, but it doesn't solve how to change the client.
Right, sure. I'm just wondering what the nature of the problem is.
Okay, so that's what I said. Okay, so the current approach to support evolution in Linux is patch. So everybody know patch here. So what is nice about patch? It's a declarative approach. So what you see is really what you get. And it's a little bit robust using that context declaration, but not so much. Basically, it works only on a single file and on a single code site. So it means that a patch file can apply only to one file. So it means that when you are doing collateral evolution, you have to have one patch file for each client code. So that's the main limitation. And even if there's some robustness in it, it's not that robust. Okay. So the result of that is that collateral evolution in Linux are done nearly manually. Even if people are using grep and Emacs, using some kind of search, regex search, it's not robust. So the result of that, it takes time. It's difficult to do, it's error prone. We discover that it may take up to several years to update a kernel, to remove deprecated code everywhere. We found many errors just because sometimes people don't understand what's going on. So you add a parameter to a procedure, people really don't know which value to put there, so they guess one. And sometimes that's not the real, the good one. And as you know, for having done a lot of driver checking tools, it's really hard to find at runtime. You may run a driver for a long time before it hit the error case. And the fact there's something quite specific to the open source model here is that many people are working independently. So they can submit patches asynchronously. So it's not rare that a patch can be out of date, or two patches can be conflicting. Some patch may miss a code side. And finally, the problem is with drivers outside the Linux source tree. And it's a really big problem for orphan drivers. So the problem is that you have a box running Linux with a specific card for some reason, and then you need to update your kernel just because a recent application depends on some library. And unfortunately, your previous driver doesn't work anymore. And you don't know how to evolve it, to make it compatible with the recent version of the system and so on. So you're stuck. Okay, so the conclusion of that is we need a tool to document evolution, collateral evolution, and we would like to automate all of this. So first thing, how are we going to specify collateral evolution? So there's a first problem, which is how to specify program transformations. And many existing approaches are imperative ones. So you really program how to do the transformation. And that's something we don't want, just because our aim is to have something that Linux developer can use very easily. So we don't want them to learn a new language. We want to have something as much simple as possible. So we want a declarative approach and something like WYSIWYG. And patch, surprisingly, is a good approach because in some way that's what does patch. You just describe how to evolve your code. The problem with patch is it's not generic. So our approach is we want a patch-like syntax, but much more generic. That's what we call semantic patches. And overall, what is the semantic patch? That's fair. This is a semantic patch, or nearly a semantic patch. So, first thing to make a patch much more generic, we're going to add meta variables. So we still have modifier like in patch, meta variables. We add a control flow operator, which is ... And it means that between these two lines, there can be some code as complex as you want. And, okay, we have meta variable references. So it means here is that here it's Y, but in fact it can be matched to whatever real variable name there's in an instance of the client code. Okay, so
this is the output of your differencing algorithm.
No, this is what we want the developer to write.
So it's like the patch spec.
I see. Okay.
So I'm going to say it again, but what we want is that the developer that does the evolution in the library, we want him to write something like this.
Okay, so it's sort of a rewrite. It's sort of telling you how to rewrite the code.
Yes, exactly.
If your code looks like this,
yes,
the ... dots being sort of wild cards.
Exactly.
Okay.
Exactly. So here we have a function. It can be whatever name you want.
So
then we are saying that the procedure returns an int, and as a single parameter, which is also an int. Then we're going to add a new parameter to this procedure, which is SCSI dot star y. There should be a variable of type SCSI, then a get, a test on the return value of the get, with some return saying that it's an error, and finally there's the put. And the minus before says that after we have applied this semantic patch, we're going to remove away these lines. So it works here both as a way to describe the context where to apply the patch, and also we're describing what we're going to remove. Yeah.
Would this example patch be designed specifically to revise a known code base, or does this sort of purport to be a general formula for evolving any kind of code that uses the old version of the library to the revised version of the library? You see what I'm asking? Like, is this like, here's a formula for taking the foobar driver written at Stanford version 12 and patching it, or is this
No.
trying to be a general solution?
No, it's a general solution for all client code that use SCSI get input.
Okay, so if it's a general solution, it seems a little alarmingly specific, right? Like, so you have this flow control operator after the test for if not why.
Yes.
What if there are side effects there, right? Where like part of that ... is to like unwind some local state, for example. And if you just toss that now, the function isn't going to behave correctly. Or like suppose like at the first ... set up some local state, or you allocate some objects or something, and the not y is an error path, right?
Yes.
So suppose in the ... that comes after the .y, part of what you're doing there is to back out some operation that you did at the first ... It's important not to lose that, right? That's error handling.
It depends.
Right, it does depend. That's the problem, right? There may or may not be something that's safe to remove at that point.
Yes, but most of the Linux drivers are developed using copy-paste, so their structure is often closed.
So that's why I asked whether this was trying to be sort of a general formula, right?
It's general. We're not pretending that it works for 100% of the drivers. Definitely.
You'll have some interesting evaluation numbers to come, right?
Yeah, it will come at the end.
So I have a couple of questions in terms of what's literal here and what's symbolic or
Okay.
meta.
So X and Y are meta.
Yeah, X and Y are meta. So so the XXX underscore info is purely symbolic. I can replace
Yes.
that with Z.
Yeah.
You're not looking, for example, for things that
Something
end with underscore info.
No, definitely not.
Okay.
It can be whatever name you want.
The other question is down here, the rest of the text. So like you've got if not why. Now, if another way that someone might say,
Okay.
if it's why not
Wait,
equal,
wait.
no, you'll.
Wait, I'm going to answer that question in 2 slides.
That's all my questions.
So since things get developed by cut and paste, you could imagine that the second green statement is appearing 3 places in the method body.
Okay.
Are you removing all 3 or just one?
So now it's not possible.
With that syntax, only once.
Okay.
Okay, that's reasonable.
All right.
We have another operator that describe it if it needs to be removed several times. If I'm going to define more precisely the semantics of ... later on. Okay, so it looks like patch, but it's much more generic. So we want to abstract details such as a difference in spacing, indentation, comments, the choice of variable name, as you said previously. We want to reason on the control flow and not on the syntax. So our tool is control flow oriented. And also we want to take care of other variation in coding style. So that's what we call isomorphisms. So your question is exactly an isomorphism. And the goal is that one semantic patch can modify most or nearly all affected files. So there are issues there also. And I will come back to them later on. Okay, so more about the semantic of the ... operator. So let's say that we have this example. So there's first a get, then a test, and we have an exit path here on the put, and then another put at the end. So the control flow is something like this. So there's you have the 2 control flow in dash lines and normal lines. So first case is 3, 4, and it's there. Goes to exit. And then you have a printf and the return here. So what we want to, in a single semantic patch, be able to remove both put. So that's exactly what does the ... operator. It means on all subsequent paths. And it applies only if there's a put on all subsequent paths. So it means that if there was not a put here, then this semantic patch would not apply.
So the semantics there is that the put is post dominating the get, but the get is not necessarily dominating the put.
I'm not
If you think of
sure to understand dominating here.
so
It says that
it's neither. So say it again. On all all subsequent paths from the get.
yeah.
There can be branches between the get and the put, as long as all branches have the put.
No, I understand that, but really, it's there can be different instances of put. So that pattern is actually right.
Okay, so yeah,
For all paths from the get, there exists a put.
exactly,
And just one.
and just one.
Oh.
Well,
Well,
Hopefully there's just one.
No, just one that involves Y.
yeah,
Yes?
That's fine.
yes, but
do you do the data flow? I mean, you do the data flow to ensure that Y isn't redefined? Is that
no. We don't have a data flow
Okay.
analysis right now. That's
Right.
one of the limitations of the actual version of a tool.
Does it match if line 4 is empty?
Yes. No. Sorry, no. Sorry.
Okay.
No.
Okay.
So, but what about multiple gets? I mean, what if I have, branching, and within the branching,
Mhm.
I have gets, and then I have one put, like the inverse
Okay,
of what you have.
so-
So here I have one get,
Okay.
I have multiple puts. What about?
Okay, so then there's another operator, but that's not the same semantics. So we have another operator I'm going to describe next that can do that kind of things. But here it's quite straight. And the interest of that is only for cases where you one put is paired with one get.
So I'm thinking of cases
And-
I've seen in code where, for example, people, based on some knowledge of the state, either get an exclusive lock or a shared lock.
Mhm.
So,
But then in any event, when
and
they're
then in
done-
any event, they're
Right.
going to release it.
Right.
But it's
No, that's exactly that case.
yeah.
You have one
It's not this
acquirer.
case. That's the other
It's
case.
the reverse of this, right? You have
It's the
different
reverse of
flavors
this.
of acquirers on different branches in one release.
Okay, but
So you have a different op-
that's
you have
the
a
same
different
case. There's one control flow, and for each control flow, there's the pair of procedure.
Yeah, it's just the reverse.
Okay.
So what's the operator for that? Is
So next slide after this one. So this one is on isomorphisms. So the idea is to be able to describe that one construct can be written in different ways. So, for instance, if you have x equal null, that's the same as saying not x or writing null equals x. Same for an if with negation. For pointer using either an arrow or a star, etc. So right now, there's no fixed set of isomorphism within the tool. The problem here is that there are an infinite number of isomorphisms. So, and it's impossible to code all of them. So our approach is to say we are interested only in isomorphism that exist in drivers. And we are going to code them in a separate file that is given as an argument to the tool. And the way we express them is based on simple. I forgot to introduce the name of a language, which is simple. Semantic path languages. So we're making joke. So it can be either simple, sample. So you can have a sample or simple sample of simple. So, okay. Yeah. So we can write isomorphism using the syntax of simple. Okay, so here is the other version of the dot operator. So what we call the nest pattern. So there's a beginning and an end. And the semantics is that there may be zero or multiple occurrence of that pattern. So it's somewhere much more flexible. But it's up to the person who writes the semantic patch to be restrict or not. So if he knows for sure that there's only one get and one put, then it's going to use the ... Otherwise, there's the nest. So on this example, there's a function copy from user that copies a variable from the user space to the kernel space. For some reason, this function was removed, and the value, it's done outside of a procedure. And the value is passed directly now to the procedure. So we have to remove copy from user, and also we have to change the way args is used. So and now we're going to assign the value of v at declarations time. So we're removing copy from user, and here you have the replacement of the declaration of v with a value coming from arg. Okay? Then we have to change all instances where the variable is used. So if we had before x dot a field, now it's going to become x, a row, and the field. And same thing for if before we have address of x, now it's x. Okay? So the result of this semantic patch, oh yes, there are two isomorphisms here. Because the test copy from user, there's an implicit isomorphism for testing for zero or not zero. And also there are isomorphisms because here you can have whatever you want before the three dots. Yeah.
So you've got this whole thing in the brackets, so it's going to match the video tuner and then match the
AGC tuner.
Yes.
What?
Okay, so the result is here.
Oh, okay.
Yeah.
Both those happen to be named V in the original source.
Yes.
What if they had different names? Would they?
Would it still match?
Would X bind to the two different names?
Yeah, definitely. So for a given match, you will stay with the same name, but if there are two instances, of course, this will be two fresh variables.
So what determines the scope of X in the patterns in the semantic patch?
Okay, the scope is the declaration. If you have another declaration later on, then it's a new scope. But within the nest, of course, it depends where the X match. So it's done basically here.
So I guess the question is, how does ... interact with lexical scoping? Because you could have multiple instances of X.
Mm-hmm.
Is that sort of the question, Chris? Like,
Do you mean nested declarations?
Yeah, nested declarations.
Nested declaration, it's a problem right now.
Uh-huh.
And it's a problem, and the answer is it's rarely used in driver code. So that's why it works. Okay?
So all the drivers for Linux are written in basically C, no C++?
No, there's no C++.
But it's only a problem if you have, it seems like it's only a problem if you have shadowing. Yes.
Huh?
It seems like it's only a problem if you have shadowing.
Yeah, right. If you have multiple instances.
Right.
But most driver writers just reuse the same old variable name over and over again. So, which causes its own problem.
Okay, here is another example, Czech region. So the history of Czech region is that it was later on replaced by request region. And there's a difference in semantics in the way that check just a check, while request does some reservation. So it means that if later on, so it's when allocating some I/O space for the driver. And what does the driver? It requests the region, and it checks if it's a real hardware it can support. And if not, it's going to release the region. So check was just checking, no request, no allocates. So it means that somewhere if you're going to release, or it's not the driver you're interested in, you need to insert a release bit before all error, before all return, sorry. So that's what we're doing here. So we're saying that we're going to replace check region with request region, and there's a conditional here is that the value x is not going to be set by any other expression. So it's more sanity check than anything else. Then
So this is x gets a value from request region and
Yes.
is not changed.
exactly.
Okay.
Exactly. Then we need to replace if x by if not x, because before x was 0 if it was okay. And now request region returns an address. So the error checking code is reversed.
Oh, it'd be nice to have some sort of, I don't know, escape or something that says, this is a piece of syntax. Because when not equal x equal e, boy. That's,
Well,
that,
I think the when is your hint, right?
okay.
Okay, that's a
Sorry,
solution.
just being the picky. Just,
Okay,
just being,
so-
just being picky. So let me just understand that. So the idea there of that when is qualifying the ... and you want to make sure there's no assignment.
Exactly.
So this is on all paths. Again, this is a control flow
Sure.
statement.
Sure.
On all paths, you should
not
not
assigned.
you should
Yes.
not see an assignment to x.
Exactly.
Okay.
Before the if.
Between.
Exactly. Okay? So we have the same here for print k. We want a print k on that path.
It says a print k must occur.
Yeah. Okay? And then we're going to add a release region before our return.
So why require the print k? So this is trying to, move code that used to use the old non-allocating one to properly release on error paths,
Yes.
right? Why require that there's a print k on error paths?
You're not forced to do that, but it's some kind of sanity check. Because most drivers, they're doing that. So if they don't do it, maybe there could be some problem. And in that particular case, we wanted to enforce a check. Of course, it's up to the responsibility. This is just an example, but this is up to the responsibility of a person who developed the semantic patch to be strict or not too strict. It depends on what feedback this person wants the tool to provide to the when the patch is going to be applied. Okay, and finally we are going to remove request region. Okay, so the result of this semantic patch is this. Okay, so how does it work? In fact, the tool relies on model checking. And we're going to translate the semantic patch into a CTL formula. By the way, isomorphisms are going to be dealt here. We're going to rewrite the semantic patch to add more cases for isomorphisms. We translate the driver code into a control flow graph. And then we match the CTL against the control flow graph. The result of that is that we have instantiation of variable with nodes. And we know exactly what are information at a given node. And using that, we're going to modify the match code and unparse it. And there's a lot of tricks here so as to be able to reproduce something which is as close as possible to the original code. So,
where does the preprocessor, the C preprocessor, show up in that?
okay.
Is that part of that?
Okay, I will tell you after. No, that's a really good question, and we deal with that in part.
Let's see you do this on an NVIDIA driver.
Okay, so why CTL? I'm sure everybody here knows CTL. So why CTL? Just because we work on graph, on control graph, and not on an abstract syntax tree. And it's really nice, in fact, when prototyping the tool, because you can easily change or test refinement in the semantics of semantic patches, but just by changing the way a semantic patch is translated into CTL. Okay, so an example. Here we have f of 1, a test, and then it's either g of 3 or g of 4. So here is the control flow graph. This semantic patch is translated into this formula, which means, so first we have an x, and for that x, there's an f of x. Then next, we need to go one step further. So that's the purpose of the AX. It just means go one node in the control flow graph. And then we want for all paths the property true until there's a y, and for that y there's a g of y. Okay, so that's the global view of a translation. Now we need to insert few things so as to be able to do modifications. So the trick, we're going to add a new variable v, and we're going to instantiate v with the value that y will have when going through the control flow graph. And there are annotations that says what we need to change in the code. So that's why there's a minus after the g, which is we need to remove g. We need to remove parentheses. And finally, we need to add g of x and y. Okay? So wait.
Yeah, I can't read this statement. Is there? You're saying you remove the semicolon?
So we're removing everything that is before the minus.
Right. So you're removing the semicolon, but then you're not adding it in. Is that a bug, or am I just confused?
Oh, maybe there should be a semicolon after the end of.
After what? Oh,
After the
The reason-
oh yeah, right.
Okay.
You're right. Sorry.
And the plus is a prefix, where the minus is a suffix.
Yeah,
Okay.
for some internal reason. Okay. So in the end, we have a witness tree, and the witness tree gives the value that variable match with, but which they are instantiated. So in fact, it's a real tree. So for x, the value of x is 1, and there are two cases depending on the node in the control graph. So first case is 3, and then v will have the value not 3, and the rewriting to perform on the control flow graph. And on the other case, for N4, the value of y is 4. So we are not just doing control model checking. We're extending it in such a way that we collect some information during the matching, and we are using it to do the transformation. Okay, so that's exactly what I said. So we bind meta variable and remember the values, and also subformulas. So what about CPP? Okay, so the trick is that there are many macros such as for each in Linux. So we treat them as, we extend C in some way to treat them as a construct of a C language. So still we have a problem right now with sharp if def, because the way this macro can be written, it can break the control flow. As long as it doesn't break the control flow, that's okay. But if it breaks the control flow, then it's a problem. So right now we don't do anything about that, but the quick solution would be to change sharp if def with real if. So this would work as long as you don't have very tricky code that fully breaks the structure of if. Okay, so we keep space indentation commands, and this is quite unusual for tools that works on C. Sorry? Yeah.
So you say you keep macros that act as patterns, whatever. What if one of your action statements are actually encoded in one of your macros? So, like, you use print statements a bunch of times. What if you have enclosed your print statement in a macro, and you have to basically open up the macro in order to do the pattern matching?
We don't do it right now. We don't do it right now.
So, okay, so if I understand, so
it's a limitation.
okay, so you basically treat, a macro that takes arguments as a function.
Mm-hmm. Yeah. As long as it does not change the control flow graph, that's okay.
I guess you could potentially write a patch that knows about.
Yes.
This isn't scalable, right? But you can say, well, these macros are commonly used. So I'll express an isomorphism.
Yeah. Okay. So again, we don't pretend that it works for any kind of C code. What we pretend that it works well for Linux drivers at the current time. We know that we think that there could be other application of the tool, but in a first step, we really want to have a good solution for our targeted domain, and then we'll see later. And we know by experience that if you try to be very general since the beginning, most of the time you fail, because there are an infinite way to write a program. just because of that. Okay, so right now we've done, we have been able to write 20 collateral evolution. That's not a lot, but these represent different cases. So we can write easily many examples that are close to this one. Some collateral evolution affect up to 130 files. So already that, it's a good result. Because if you process that amount of file manually, but it's likely you're going to forget one or two. And the compiler does not always detect problems. It worked for 70 up to 100%. And it's reasonably fast. It's not, it could be improved. Personally, I think it would be very interesting to try to parallelize that, so as to be under 1 second for most of the patch, so as to be much more interactive.
Sure, but 2 seconds less time than it would take a programmer to edit the file. Right? I mean, this is really what you're comparing it against, right? It's not.
No, it's too good for one file. So if you
I know, but there's no programmer on Earth, no human is going to edit those files in 2 seconds per file, right? Which is really what your competition is.
Barely open in 2 seconds.
Yes.
Oh, yeah, you're perfectly right, Galen. No problem with that. It's just the way we see the tool is to be integrating in some kind of interactive environment. So you need to be quite fast to provide feedback to the user. That's all I'm saying. Of course, you're perfectly right.
So how did you evaluate success?
Okay, so we are doing this to well-known collateral evolution, so we know the result.
So you have the before and after in the real Linux tree.
Exactly. So we're able to see if it was done correctly or not in Linux. Because sometimes we fail, but we also discovered that sometimes they failed.
So curious, do you like literally do a text compare and see if there's the same? Are you hand looking at to see if there's the same?
We are looking at the C.
What?
We are looking at the C code.
Okay.
And
Therefore by eyes.
Yeah, how are you doing it?
Manual inspection. We don't have a...
So you're looking at each of the transforms and reasoning whether it was correct.
Yeah.
Okay.
Yeah. That's a lot of text processing right now.
Yeah.
As I said, doesn't work for all cases. Sometimes doesn't work, and the reason are CPP issues. We know it's a problem. We know we will never be able to treat 100% of the cases. Our aim here is that even if we fail, we want to warn the user and tell him there's something wrong here, and you should look at it. We're lacking isomorphisms, and sometimes it would have been nice to have data flow isomorphisms, but it's really not simple to handle. There are complex issues there. If you have x equal 1 and then f of x, how do you evolve that? So are you going to change the value of x everywhere? What if there's some other treatment between? There's no really simple solution. Yeah.
Okay, so presumably you took one snapshot of Linux and then another snapshot of Linux, and you worked across that delta.
Mm-hmm.
You've done 20 collateral evolutions. So, okay, you say some of them affect up to 130 files.
Yes.
Total, how many files have you? Have any idea?
I need to check it in the paper.
Do you have any idea how many more collateral evolutions there are in that delta? I mean, did you?
Okay. I have some numbers about the number of collateral evolution there are between versions of Linux. There are much more. So what we've done before was this extensive study of collateral evolution, and we have studied manually more than 90 collateral evolution. So we know exactly for these 90 cases what should be done. We discovered many errors. So our first goal is to
20 of those 90 then.
Exactly.
Okay. All right.
So, and between these 90, there are common cases also. But we think right now they're representative enough.
So is 90 the total, or do you think maybe there will be 1,000 collaborative evolutions?
There are thousands. I will show you some numbers after the end of the talk if you're interested in it. Okay, so oh yeah, our vision. So this is one vision. There could be several ones, but the idea is that there's a library maintainer. He performs the evolution and he writes the semantic patch. Then is going to check that the semantic patch works on few files, and it's mainly an interactive job, as I said before, an iterative job also. When he's confident, he sends it to Bill, no, Linus, an easy way. And so, strangely enough, that's Linus that approve most of the patches. And so Linus will apply it to the latest version of Linux. And also, the problem is the newly added code and drivers. So you can write, you work, on a version of Linux, and you know for sure it's already outdated. So it means that when you merge your change with the up-to-date state, for sure there will be some problem here. And finally, semantic patch is put in a global repository that is available to everyone so that they can update their own driver. So one thing we would like to do is build a repository of the evolution of Linux since 2.4. That's one of the future work. Okay, I'm done. Conclusions. So collateral evolution is an important problem, at least in Linux drivers. We have designed a declarative language, simple, which I think is simple enough to be used by Linux programmers, and we don't want to force them to learn something new. So stay as close as possible to what they already know and what they master. So our solution works, is control graph oriented. It does not work just on the syntax, so that's why we call them semantic patches. And we have a transformation engine based on model checking. And questions, if you have some over. So why Coccinelle? Okay, it's ladybug in French, and it's just a bug that eats smaller ones. And so one side objective of a project is to prevent bugs to appear when doing this collateral evolution problem. Okay, so if you want some numbers. Okay. This graph shows the number of evolution from Linux 2.2 to 2.6 in the number of libraries. So here you have the number of interface change. So you can see it grows up. The only reason there's slightly less in 2.6 is that 2.6 is much more recent than 2.5, which evolution on 2.5 are done, while it still evolves on 2.6.
Okay, so is each of these from 2.2 or
Or from the previous?
or from the previous one?
No, from 2.2.
Oh, okay.
So that's why it keeps going up.
So when it went from 2.5 to 2.6, you actually undid some changes, is what this graph
Yes.
tells us.
Yeah.
So if there are less changes
Yes.
from 2.2 to 2.6 than there are from 2.2 to 2.5, then some of the changes that were introduced in 2.5 must have been reverted.
Why? Why?
So did you just tell us
Or
that,
did-
that each of these bars is the number of changes compared to 2.2?
No,
No.
no, sorry.
It's
Not
from the previous
cumulative.
one.
Yeah, from the previous one.
Okay. Okay.
Sorry.
So there were roughly 400 changes from 2.3 to 2.4.
Yeah.
That's right.
Yeah.
Now, okay, and these are, how are you counting these? So this is, so if someone changed this, that one thing in the SCSI,
Mm-hmm.
okay, are
Is
you
that
counting,
one?
is that one, or is that, well, it's used in 100 SCSI drivers, so it's 100?
No, it's one. Well, it's the number of evolution, not collateral evolution. Uh, these are the number of collateral evolutions in Linux patches. So you can see it's increasing both in percentage and number of lines. Where is this? I have another interesting. Okay, can't find it. Sorry.
It's like, sorry.
Yeah. Okay, these are the, for each specific file, the number of library used.
Number of different libraries?
Yes. So it's up to
6.
7. And you can see that most in 2.6, about 100 device-specific files, they use 3 libraries.
And those other graphs tell us functions, so
Yeah.
sort of tens of functions.
Yeah.
Well, should we thank the speaker?